students, welcome to the online lab practicals of digital communication. First of all, we would see the practical list, but before that, we would see the outline of the lab practice. So basically, guys, this lab practice, it is for third year engineering students and it has total 2 credit points. So examination scheme, basically this practical, it is of 50 marks and it carries a term work of 50 marks. And this lab practice of digital communication, it is combined with your signal processing, that is DSP subject. So together, signal processing and communication, they made one lab which has a credit points too. So in your examination, either you have to perform a practical from DSP or digital communication. Since these are the list of practicals that I already explained in my outline while we discussed the outline of the subject. So these are the list of practicals that we want to perform. And these are the practicals that we have to perform the simulation. So without much wasting your time, we would start our first practical, that is a verification of your sampling theorem. What is our aim? So basically, guys, aim is to study of sampling and reconstruction of its signal. The apparatus that we required, it is your Scientech kit, CRO, and your connectors and probes. Now guys, the signals that we use in the real world, such as our voice or audio signal, they are called what? Analog signals. And to process these signals for digital communication, we need to convert analog signals into digital form. While an analog signal, it is continuous in both time and your amplitude. A digital signal, it is discrete in both time as well as amplitude. And to convert this continuous time signal into discrete time signal, a process is called as sampling. We have to use it. And the value of the signal is measured, at a certain interval in time, and each measurement is referred to as what? A sample. Now, what is the principle of sampling? So consider a guy's information signal. See, theory I already covered in the lecture. So just a brief introduction I'm going to give it. This is your analog signal x of t that we want to make it into what? Discrete time. So we are going to apply this x of t, that is a continuous time signal, to this sampler. It is a switch basically. So it is going to obtain the points, obtain the sampling at a particular instant of time, which is called a sampling period. So at a particular instant of time, if I'm going to take the samples of this analog signal, the output we would get what? Sampled output. So let's start, guys. This is a Scientech sampling and reconstruction trainer kit. This section, it is your sampling frequency selector circuit. It is there. This is your oscillator. And we are going to generate a sampling frequency at a different rates, 20 kilohertz, 40, 60, then it is 160, 320, as like that. And this is my signal which is available at what? 1 kilohertz, 5 volt peak to peak. The frequency is a signal whose frequency is 10 kilohertz divided by this 10 frequency divider circuit, and at the output, this is your test point. So at the output of this, we would get our continuous time signal, that is x of t, which is of 1 kilohertz, 5 volt peak to peak. This is the switch, guys, by which you can select the sampling frequency, and the LED would glow. The desired LED would glow depending on the selection of that frequency. The output of this multiplexer, it is given to this duty cycle controller circuit. By means you can control the duty cycle of the sampling pulses. After that, it has been given. Now, this is your second section. Now, third section, it is your what? It is your sampling selector. That is your natural sampling and it is your sample and hold amplifier. Sample, natural sample amplifier and sample and hold amplifier. As guys in theory we discussed, there are three types of sampling: ideal sampling, natural sampling, and sample and hold sampling. So basically guys, since ideal we are not going to use it because practically we couldn't use that one. So we are going to show it what? Natural sampling and your sample and hold. So what we are going to do it, this is the switch, that is you can do it, take it as an internal sampling pulses, or when you are going to make this switch to this left hand side, that is to external, you can apply a external sampling over here also. So you can have a two outputs, that is a natural sampling at this test point and the sample and hold output at this instant. Now guys, after sampling, the output of the sample you would get in discrete in nature, that is a PAM, pulse amplitude modulated wave. Now, in order to recover these sample, that is your original signal from your samples, we have to apply it to the low pass filter. There are two low pass filter it has been given, that is a second order Butterworth low pass filter and it is a fourth order low pass filter. It is a Butterworth filter. So you can either apply to any of the filter, and at the output we are going to measure, we are going to observe the waveform, that the waveform that is being transmitted from here and the waveform that we received are same or not. So guys, we would now see the step by step procedure that how to perform the practical. So first we are going to connect the input waveform, which is of 5 volt peak to peak, 1 kilohertz. This is your x of t. It is going to apply to your this signal input to this amplifier. So by means of selector switch, we have kept it to the internal switch, and at the output we can get the sample waveform. So see, you can observe the waveform. Now we have the output of the natural sample amplifier, we are going to observe it now. And you can observe it now, the sampling frequency, it is of what? It is of now 40 kilohertz by selecting this switch. Now guys, first task is to observe this input waveform on your CRO. So we have connected one channel to this test point number 12 in order to observe what? Your input signal, and the ground it has been applied to this. After this one, see guys, we have connected to this channel 1 to this CRO. When you will observe it, this is your input signal, which is of what? 5 volt peak to peak at 1 kilohertz. After this, now what we are going to do it, we are going to connect this second channel for what? In order to observe the output of this sampler, and we have connected to what? Natural sampler. So there are two channels now. So keeping this mode on this dual channel, you will get the waveform like this one. See, this is your input signal and this is the output of your sampler, that is a natural sampler. See the shape, you can observe it. The shape of this output of this natural sampler, it is going to retain the shape of this input signal. Although you can observe it, there is a phase lag, there is a lagging. The output signal, it is a lagging behind this input signal. So it is going to retain the shape of your instantaneous value of your input signal, and hence it is called as what? Natural sampling. Now guys, if I am going to increase the bit rate, earlier it was what? 40. Now if I make it to 80 kilohertz, see the number of samples, it has been increased. You can observe it over here. Number of samples increased. Now from 80 to 160 kilohertz, see the number of sample, it has been increased. So the output of sampler, that is a natural sampler, it is almost it is gets resembled to your input signal. And similarly, if it is a 320 kilohertz, see the output of the sampler, it is almost similar to your input signal. So hence we can say that this is going to prove, the Nyquist rate. What is that Nyquist rate? That the sampling frequency, it should be greater than or equal to twice of the highest frequency of your input signal. So number of, the sampling you are going to increases, it would be helpful to recover these input signal from this sampled signal. Now guys, now we have seen the output of this sampler. Now it's tasked to what? To apply the output of the natural sampler to this second order low pass filter. So when you are going to apply this to the low pass filter, now we are going to see that how would be the output of the low pass filter it would see. Now see, by disconnecting this second channel, now we have connected the second channel of CRO to the output of this low pass filter. So you can see how the output of this low pass filter it is there, and why it is in the form of your square wave little bit, because sampling frequency we have selected, it is what? 20 kilohertz. If you are going to increase the sampling frequency to 40 kilohertz, see the output of this low pass filter, now it is little bit, similar to your input signal, but not exact. But now if it going to make it to 80 kilohertz, see now it is going to try to catch this waveform. So what the information we send, the similar kind of information we are getting received. Again, you are going to increase the sampling frequency towards 160 or 320 kilohertz. You can observe the output, it is recovered. The output of the low pass filter, it is almost same as of the input that we have transmitted. So it is about what? Natural sampling. Similarly guys, now we are going to observe it what? Sample and hold, that is a flat top sampling. So you can observe the top of the sample, it is a flat, because we are observing what? Output of your sample and hold amplifier, that is a flat top sampling, it is there. So the frequency that we selected, it is a 40 kilohertz. So see the sample. Now if I am going to increase to the 180 kilohertz or 160 kilohertz, see the number of samples it is going to increase, and the output, that is the top of the pulse, it is a flat, so that the noise, it could not be easily added to the top of this pulses that we already studied. And see when the 320 kilo or 160 kilohertz it has been applied, see how it is going to resemble to this original signal. And again, the output of this flat top sampling, it is going to apply to this low pass filter, and we are going to observe the output of this low pass filter. So what I told, it is your recovered one. Why is it so? Because sampling frequency, it is low, almost it is 20 kilohertz, 40 kilohertz, this is the output. And for 320 kilohertz, see the output of the low pass filter, this is of switches get similar to your input signal. Now guys, we are going to see the video of how we have done the the practical. This is a sampling and reconstruction trainer kit. This is a sampling and reconstruction trainer kit. This section, it is your analog signal that we want to sample it. So it is available 1 kilohertz signal, it is available over here. And you can see it is a sampling frequency selector switch. By selecting switch, you can select the sampling rate of 20 kilohertz, 40 kilohertz, 80 kilohertz, 160 and up to 320 kilohertz. So guys, right now what we have to do it, since this is a input which is going to generate an input, and this is your sampling circuitry. This is your sampling circuitry. So what we have to do it, we have to connect this 1 kilohertz sine wave and we have to give to this input signal over here. And this is a switch that it is a selector switch. By default you can make it to internal only, and there are the two sampling output. You can see it over here. It is a sampling, that is a natural sample over here, and it is a sample and hold amplifier, it is there. So now this is the CRO. First of all, what we would do it, that we would connect or we would observe this input signal. So I am going to connect this input signal to this pin, and a ground, it is connected over here. And you can observe it. This is your analog wave, that is we want to sample it. So now guys, we are going to see the sampled output, the output of the sampler. So for that purpose we can take the second channel and you can connect it to the output of your sampling amplifier. So this is your sample output. We have connected to the second channel. So make it to dual one. So you can see the above signal, it is your analog wave, and this signal, it is your sampled signal. And you can see it on the kit, the sampling frequency, it is of 20 kilohertz. Now we are going to increase it. So make it to 80 kilohertz. So you can observe this one. How it is going to sample it. See the sampling rate, it has been increased. See. So if we are going to increase the sampling rate, the sample output will be more resemble to your input signal. This is your input signal and this is your output signal. So as we are going to increase or decrease this sampling rate, the accuracy of the sample output, it would be more and more closer to this input wave. See at 320 kilohertz, how is the output? It is very much closer, similar to this input signal. Now guys, this is the sampled output. Now we are going to see what happened when the output of the sample, we are going to connect it to this low pass filter. So over here now, we are going to connect this sampled output to the low pass filter. Now we are going to observe the output of this low pass filter on the channel. So you can see guys, this is the upper signal, it is your input signal, and this is your output of your low pass filter. But it is when the sampling rate, it is very high, that is 320 kilohertz. But you can see now, if I am going to reduce the sampling rate, see it is at now 40 kilohertz, how this output of the low pass filter, it is going to appear. So this I want to tell you, if you are going to increase the sampling frequency, see the output of the low pass filter, it is going to resemble to the input signal. Now guys, we would see the flat top sampling. This is a sampling and reconstruction trainer kit. This section, it is your analog signal that we want to see. Now we have seeing the output of the sample and hold amplifier, and the sampling rate, it is at 40 kilohertz. It means it is a low sampling frequency. So now you can see the how the output it good looks. So you can see on the CRO, see it is holding, the holding the output, since it is the output of your sample and hold operation. So now if I'm going to increase the sampling frequency to your suppose 160 kilohertz, so you can see it over here. So how this sample and hold output, it goes closer to the your input signal. Now similarly, the output of sample and hold, now I am going to connect it to your low pass filter, and we are going to observe the output of your low pass filter. Now you can see more clearly, this is your output of your low pass filter and this is your input signal, how it is very much been achieved by means of low pass filter, but keeping your sampling rate at 160 kilohertz. If you want to know that we are make it to only 40 kilohertz, then see the output how it is going to look. So sampling, it is basically totally depends on your what? Sampling rate. So we have seen the output of natural sampling and flat top sampling. So we have sampled a continuous time signal x of t and we have recovered back from low pass filter. So sampling theorem, it states that a continuous time signal, it can be completely represented in its sample form and recovered back from its sample form if its sampling frequency is greater than or equal to twice of Fm. So thus we have studied our sampling theorem. Thank you very much, guys.